So, welcome everyone, and thank you for joining. We are here for Container IMA using eBPF by Lily and Avery, and we'll get started now.
All right. Hi, everyone. Thank you for joining our session. I am Lily Sturmann. I am a software engineer in Red Hat's Emerging Technologies branch in the security team, and I am here with Avery.
Hi, I'm Avery. I'm currently finishing up my undergraduate degree at Columbia, studying computer science, and I have been an intern in the Emerging Technologies department at Red Hat since about May of 2022, and I'm excited to share my work with you all today.
And I want to say this is a collaborative project with the Emerging Technologies networking team, as well as IBM Research. And I want to give a huge shout out to Dave Tucker and Arnaldo DeMello, who were helping us debug some eBPF stuff yesterday. So yeah, we have a lot of good people working with us on this project. So this is going to be the flow, which hopefully won't surprise you. So we'll talk about our motivation for this project and some of the background technologies that we're going to be using. And we'll talk through the threat model and implementation and some of the future work that is yet to be done. I do want to say this is still a work in progress. So yeah, actively under development. We're basically sharing with you some of our design details today as we continue to build this out. So thanks for being with us for this part. So this is basically motivated by our work on the Keylime project. If any of you are familiar with Keylime, you will know that it's a remote attestation framework. So this is something that is now available in RHEL, and it is also upstream work. What it does is it allows you to verify machine integrity on a remote system. So the use case here is important for hybrid cloud or edge scenarios where you might be running workloads on untrusted infrastructure, and you have some connectivity to that infrastructure from a separate trusted control plane. So Keylime will enable you to make sure that the machines or devices that will be running your workloads boot in the expected state, and also that during runtime, the state stays what you expect. Keylime can handle both of these scenarios, so boot state and runtime state integrity, and it does this using a TPM or a VTPM or software TPM where applicable as a root of trust. And it also relies on using the Linux integrity measurement architecture, which is part of the Linux kernel. So basically the remote system that you see on the left here is emitting all these hashes, which we'll talk about in a little bit more detail on one of the next slides. That is the chain of trust routed back to the TPM. And it's sending all of these values over to this verifying system, which is able to check them with the help of Keylime. So this is great, but the current limitation that we're seeing is that Keylime is not able to do this for individual containers separately from the host. And this is actually something that is inherent in the integrity measurement architecture, or IMA, because basically, IMA doesn't have a separate namespace for containers and can't distinguish between the two. So there is actually a set of patches going into the Linux kernel right now to help distinguish between those. But in the meantime, we were wondering if there is anything that we can do to get this information a different way. And using eBPF provides this visibility and this separation for IMA while requiring no changes to the Linux kernel. So that is pretty exciting. That is actually the key advantage here. And we are still in the experimental phase with providing a proof of concept here. But if it does work, then that will be a very cool shortcut for us to be able to do this and extend Keylime attestation to individual containers separately from the host. So that is our motivation for this project. And we rely on 3 main technologies to do this. So the first one is IMA, which Keylime integrates with, and which also can rely on a TPM. So what IMA does is that it measures files on a system and then detects if they have been altered. So by a measurement, we mean a hash of a file that can be compared to a known good or previous value. And this is supported in RHEL 8 and above. It's been part of the Linux kernel since, I think, version 2.6 or so. And for our purposes, it is important to know that IMA can be anchored in a TPM. That's how Keylime uses it. And this can be used to verify the system's runtime integrity. It's also important to know that IMA hooks into the mmap system call, which includes a call to IMA. So that is why when we discuss our implementation in the next few slides, we're going to be mentioning the mmap system call. The next technology that we're relying on is the TPM. So TPMs are available in many machines today, often used as a hardware root of trust. The hardware component provides better tamper resistance and tamper evidence than pure software implementations, but TPMs are also available as virtualized TPMs and software TPMs where hardware TPMs aren't available. And Keylime can work with all of these types. So the TPM has various cryptographic functions that are often used for attestation of a system's boot state. For example, if you think back to the previous slide where that remote system was emitting a chain of hashes or a chain of trust, this is a little more detail on what that looks like. So each component in the boot chain is measured. So that measurement is a hash of some event that happens. And then that is concatenated with the hash of the next event. And this concatenation is also hash. So it builds up something called a Merkle tree. And this is signed off on by the TPM's private key to ensure authenticity. So you basically get this chain of events that goes all the way back to the root of trust and forms an immutable record of the system state. The third technology that we're relying on is eBPF. This is that exciting portion that we're including because you can basically make dynamic changes to the kernel. So eBPF allows you to run programs inside the kernel dynamically without changing the kernel source code. And this adds additional capabilities to the operating system at runtime. This is often used for observability, for example, tracing the execution of applications through kernel space or advanced load balancing in networking applications. And it is a very cool technology that's worth checking out. And now I will pass it over to Avery, who will take us through the threat model design and implementation that she's been working on. I do see there are some questions coming in, so we will try to get to those at the end. Thank you for submitting them and participating. Avery?
Hi. So the goal of this project is to detect remote and local software attacks that aim to compromise container file integrity. The solution does not attempt to protect the container or the system against such attacks. There are many different examples of attacks on file integrity, authenticity, and confidentiality. For example, the execution of malicious code and offline attacks. This project also assumes that the host operating system is trusted and that attackers cannot gain ownership of the trusted platform module. Next slide, please. To provide container integrity measurements, the solution must provide a separate immutable measurement list rooted in hardware and must not hinder the scalability that is central to container-based virtualization. The requirements for this project can be summarized as followed. Container IMA must provide the same functionality as IMA and provide the same interaction for remote attestation as IMA does. This project should not affect the host IMA process, and the architecture should not impede the host ability to scale. Each of these containers should also be strongly associated with their IMA resources. A goal of this project was to utilize as much as the existing IMA API as possible to extend the architecture to containers. Some of these functions, however, could not run unmodified and were rewritten to allow for the separation of individual container IMA resources. Maintaining separate container logs and resources allows for the host IMA process to remain unaffected by the inclusion of container IMA on the system. In addition, the software should not impede the scalable nature of containers. As TPMs have a limited number of platform configuration registers, scaling and IMA appear at odds. So to satisfy this requirement, each container will have its own emulated software TPM. The use of per container TPMs also allows for deeper separation of container and host resources. A container identifier is used to allow for individual container IMA resources. In this project, I used the namespace of the task struct calling IMAP. This identifier is included in all the resources to allow for an association between a container, its resources, and its logs. Next slide, please. So the implementation takes the form of a kernel module and an eBPF probe. Having the code running kernel space allows for access to kernel resources and libraries, as well as the ability to log in the desired location. The eBPF program hooks into IMAP to provide visibility into the executable content of a container. To initialize the program, the process measurement function is exported using libBPF for use by the probe, and an attestation will be carried out to ensure that the probe has integrity and extends trust to the probe. The IMA resources are namespaced and the measurements are extended to the container software TPM. Next slide, please. So the idea of trusted IMA relies on that the kernel is doing the right thing. So implementing this project as a signed kernel module allows for the module to be signed and included into a securely booted kernel. The inclusion of this module in a secure boot system extends trust to that kernel module and then measures the integrity of the eBPF probe. The eBPF probe provides visibility into the IMAP function without making changes to the Linux kernel. The eBPF probe provides crucial visibility into the executable content of a container that our project then uses to carry out integrity measurements. Due to the implementation of IMA, leveraging the existing eBPF system call hook into IMAP allows for us to follow the same structure as the normal implementation. Next slide, please. Yes, that's the right slide. So the probe was designed to find an IMA solution for containers without changes to the kernel. The main idea was to explore the feasibility of using information gathered by an eBPF probe into IMAP and use it to measure file integrity. As the eBPF probe provides the same visibility into the executable content of a system as IMA has in the kernel, the probe provides all the necessary data to measure system integrity. The probe is basically an eBPF program that hooks into IMAP. We use the libBPF library. In October of 2021, a patch was merged that allowed for eBPF programs to use functions defined in kernel modules. This patch allowed for our design. So the probe calls a kernel module function, which carries out the integrity measurements using the parameters which were passed to IMAP. The IMAP probe provides visibility into the system call, and that is then used to measure the executable content, and the namespace of the task calling IMAP is used as this container identifier. Next slide, please. So a kernel module was used to gain access to kernel space, resources, and information, as well as providing a solution that can be securely booted into a secure boot system. The kernel module carries out all the IMA functionality. This functionality can be split into three different parts: initialization, measurement, and storage. And the initialization portions of the module, the per container IMA data structures are created through throughout the sections, and they're stored for use throughout measurement and storage. These structures are initialized here to allow for the separation of sensitive data. Containers have private structures for tracking inode integrity, storing digest, and interacting with their TPMs. The kernel module initializes and keeps track of private data throughout the measurement event. In the measurement section, a file and inode information is queried for storing and tracking of integrity measurements. The measurement is a cryptographic hash of a file and is extended to the container's virtualized TPM. The hash is then stored in a template alongside other data for logging, and these templates are used to ensure that measurement logs maintain the same structure as standard IMAs. To ensure the probe is trusted, the kernel module will have the probe attest to the module before it is inserted in the kernel. This verifies the integrity of the probe portion of this project. Next slide, please.
All right, so this is the portion where I want to plug our future demo. This is a teaser for the demo that we're going to have. So if you're interested in seeing this, please do send me a message on GChat or an email. And I want to make this into a fun separate event. So let me know.
So as this project is still a work in progress, there are numerous opportunities for future work, both to address existing issues that we're working out and to implement new functionality. For instance, in the current implementation, I don't allow for each container to have separate IMA policies. So to provide the full IMA functionality and customized policy for each container, the current solution will need to be adjusted for parsing and storing different policies. We will also be working on some benchmarking, as well as looking at how this scales for IMA to scale horizontally on a system through the use of containers. We also currently do not implement IMA appraisal. The appraisal functionality for IMA stores a good file state and appraises the current measurement against this known good value. So we'll look at implementing that in the future. So just kind of as a summary, in this project, I leveraged the kernel's existing support of the eBPF to extend the Linux integrity measurement architecture without changes to the host. I would like to thank everyone that came to this presentation today. I would also like to thank Professor Jason Lee, who advises this on the Columbia side, as well as everyone at Red Hat who's helped throughout this project.
Yes, thank you all very much. I see there are some questions. Yeah, so about the demo, or if you want to get in touch, definitely send an email, even if you are not Red Hat internal. If you are Red Hat internal, you have a few options in addition to email that you can utilize. So thank you for asking about that. We have another good question. Can this be used with rootless containers? I think right now, no, but I can see why we would want to do that. Unless I'm wrong, Avery. We've been using root.
Yes.
Yeah, that's a very good question. So we could stick that on future work. And as you can see, we've got a design going, but we are still kind of building this out. So if you have any other ideas for things that you'd like to see or that would be important, definitely plug it in the chat, send us a message, things like that. There's definitely still time for working out some of those details. So yeah, any other questions or thoughts? We're happy to field those, or if not, we're available afterwards also. I think we can also hang out and wait.
Yeah, we have a little bit more time, so if anyone wants to ask questions, please do. Yeah, there's one other question.
Are we using a container runtime in any specific way? I don't think so.
No, we are not. This is mostly all taking place from like the operating systems level.
Do you have any thoughts on any details specific to specific container runtimes that you'd like to see? Or if there's anything you're thinking of?
If anyone wants to come off audio, come on audio or video, please let me know. So, looks like no other questions.
That's fine too.
Yeah, there's one. What would be possible to do a remote attestation that are
so there's kind of a multi-part answer. We're looking to integrate this with Keylime. And Keylime as a remote attestation framework doesn't block anything from running. So it wouldn't block runtime modifications, but if something did run that was unexpected and potentially malicious, there are configurable revocation actions that can be taken with Keylime. But yes, basically it would run on a container level, and it would be able to distinguish anything running in a specific container from the host. That would be the novel feature there. Does that answer your question? Yeah, and we do welcome anyone coming off of mute as well.
Lily, there's a follow-up to your.
Yes. Cool. Yeah. Yeah. So the way Keylime works is that it detects a compromise. For example, at runtime, if you run a malicious script, you as the attacker in this case, Keylime can detect that. And it will be after the fact. So it's not blocking execution. That's not really what the framework is intended to do. But this is usually used in kind of a cluster setup. So for example, a revocation action could detect that one of the nodes machines or devices is malicious. And so a revocation action in that case could exclude that from the rest of the cluster or something like that.
Thank you. And there's a question from Brian. How is this different from a solution such as Falco that relies on eBPF?
Honestly, I'm not familiar with Falco. So unless you are, Avery, that is something we can follow up on. That's also a good question because we want to compare and contrast and differentiate it from existing tools for sure.
I know only a small amount about Falco. I think kind of the main difference here is the goal. So the way that we use eBPF is more as a way to extend IMA to containers rather than kind of having a whole system that monitors system calls. But I do know that they both operate like Falco has the user space and kernel space solution for interpreting and monitoring system calls. So I think the main difference here is the intended use.
Thanks, Avery. Let's see. Next question asks, can you talk more about policies? Actually, I should have been reading these aloud to begin with because I don't know how this will be rendered after the fact. Can you talk more about policies? What do you have outside the box and how easy is it to customize the framework? It is supposed to be very customizable and configurable. So in Keylime specifically, I think there's current work undergoing to revamp a little bit of how the policies work, but you can submit your own runtime policies as well as your policies for the measured boot. And then all of the revocation actions are totally configurable. So it gives you a framework to work with, but everything is very specific to your system and what makes sense for you, what kinds of malicious actions you want to look for, what you want to ignore. For example, you don't want to flag everything that happens in var log, for example. And yeah, so the specific things that are tailored to your system and environment, those would be outside the box. And Keylime sets up the framework for you to be able to use all of this. It gives you the attestation components with the verifier, and it gives you the ability to have these revocation actions while hooking into the TPM for that integrity.
There's a follow-up.
Here's an example from Competitive Commercial Solutions and mentioning Sysdig. Yeah, that's interesting to know about. Thank you. I will have to look at that.
Do you plan to integrate with current system TPM work?
Not yet, but if you can give us some good reasons to do that, we could certainly stick it under future work.
Any other
Thank you, everyone, for all the questions so far. Yeah, these are great. We really appreciate it. This is going to give us some good ideas as well as we flesh this out more.
All right, seems like that is the end of the questions. And thank you, Lily, for your session and answering all the questions.
Thank you for moderating, and thank you everyone for attending our session. Definitely send me a message. I would love to talk more. Send Avery a message. Thanks, everyone.
Thank you.